Okay, so our next speaker is famous mathematical physicist, is that right? Or
non-famous.
or physicist or mathematical physicist or mathematician. Sunghyuk Park, who came all the way from Cambridge, Massachusetts, from Harvard University, and will tell us about 3D quantum trace map.
Thanks for the introduction and thanks for inviting me to speak here. So in this talk, I want to talk about my recent joint work with Sam Panitch, constructing the 3D quantum trace map. So it's this homomorphism that relates two different quantizations of the character varieties of three manifolds. One is the Kauffman bracket skein module, which we've already seen in a few talks yesterday. And the other one is something that's sometimes known as the quantum gluing module, which is a module or a vector space that can be assigned to a three manifold equipped with an ideal triangulation. So I'm going to first give an overview of what these objects are. I'm going to mainly focus on this the skein module part and just give a brief. I'm going to explain briefly what this quantum gluing module is, and then I'm going to give the main idea of the ideas that goes into the construction of this map. So let me be very brief, since we've already seen what skein modules are. So throughout this talk, Y is an oriented three manifold, and for now, let's work over the ground ring, which is the Laurent polynomial ring in one indeterminate A. Or sometimes it's more convenient to work over the field of rational functions. The Kauffman bracket skein module, which is also sometimes called the SL2 skein module, since it's based on the quantum group of SL2, is the free R module spanned by isotopy classes of framed unoriented links in Y, modulo the skein relations. There are two skein relations. Here, the first one is basically allows us to resolve a crossing. It expresses a crossing in terms of a linear combination of two resolutions. And the second one allows us to evaluate the trivially framed unknot to some number. So here are some basic properties of the skein module we've already seen in the talks yesterday. The first basic property of the Kauffman bracket skein module is that the skein module of S3 is non-zero, and in particular, it's a free R module of rank 1 spanned by the empty skein, meaning any knot we have in S3, we can use the skein relations to express it as an empty knot times some number in R in the base ring, and that's this number is also called the Kauffman bracket polynomial of the knot. When our three manifold is a surface times interval, then because we can stack the surface times interval along the interval direction, we can stack one on top of another. That gives an algebra structure to the skein module, making it a unital associative algebra, with the unit being the empty skein. And in this case, the skein module is also called the skein algebra of the surface, sigma. And I'll use this notation, SKL, just to distinguish that skein algebra is something associated to surfaces, whereas skein modules are associated to three manifolds. And by the same reason that we can stack surface times interval on top of the surface sigma, for each boundary component sigma of y, since we can stack this surface times interval on the boundary, the skein module of y is a module over that skein algebra of the surface. So these are all basic facts. Yeah, we've already seen this. Another important property of skein module is that when we specialize this variable a to be either +1 or -1, then what was initially just an R module becomes a commutative algebra, which is because in this skein relation, if A is the same as A inverse, then the skein relation does not distinguish overcrossing with undercrossing. So it doesn't matter. So the skein module doesn't see the knottedness. And because of that, given any two skeins in this skein module with a specialized variable, given to any length, we can superpose one on top of another, and that still gives a well-defined map, product map, making it into commutative algebra. And yeah, in this case, this commutative algebra, especially when A is -1, that's known to be isomorphic to the coordinate ring of SL2C character variety of Y. Yeah, and also another fact that was already mentioned by Rhea, that even though we won't use it, just a very nice recent result by Gunningham, Jordan, Safronoff, that for when Y is a closed three manifold, then it turns out to be finite dimensional over a field of rational functions in A. Okay, so that was a lightning review of what probably most of you are familiar with. For our construction, it is important to study a relative version of skein module, meaning we want to study skein modules by cutting our three manifold into simpler pieces. The relative version of skein module is known as the stated skein module it's called stated for a reason that will become clear in a moment. And the earliest version of it, I think, appears in this work of Bono and Wang that relates skein algebra of surfaces with quantum tabular space. And and the definition was refined by Lei and Constantino Lei, which I will review right now. The definition I'm going to give is actually a slightly generalized version, which we need in our construction of 3D quantum trace map. It's going to be slightly different in a sense. Let me first give a definition and let me tell you how it's different from the previous definitions. Okay. So again, let Y be an oriented three manifold, and we'll also put in some extra data, which is a graph on the boundary of Y. So in this cartoon, let's say Y is some three manifold with boundary. We're going to draw some embedded oriented graph, gamma, on the boundary. And we want this oriented graph to be such that all the vertices are either a source or a sink, meaning the orientation at the edges are such that for each vertex, the orientations are always coming out of that vertex or coming into that vertex. If it's coming out, it's called a source. If it's going in, then it's called a sink. So this is an example of a boundary marked three manifold. Please don't hesitate to interrupt me if anything is unclear in this talk. Okay, so given a boundary marked three manifold, a stated tangle is an unoriented ribbon tangle or frame tangle in Y, such that the endpoints of the tangle lie on the boundary marking. And it has to lie flatly, meaning the framing must be tangential to the boundary marking. And we're also putting in a function from the set of boundary points to the signs, which we call state. So it's just an assignment of signs plus or minus 1 for each boundary point. And that's called a stated tangle. Now, the stated skein module of a boundary marked 3-manifold, y comma gamma, is defined in a way that's very similar to how the ordinary Kauffman bracket skein module is defined. It's first we take the free R module generated by isotopy classes of stated tangles, and we mod out by stated skein relations, where the stated skein relations are given by the following relations. So the first two are the ordinary skein relations in Kauffman bracket skein module that we saw earlier. This last one, I mean, it's not necessary. I'm putting it just for simplicity. So, so here I'm allowing my tangle. So when I call a tangle a ribbon tangle, I actually mean that it is framed. Okay, it has a how to say? Yeah, it has a framing up to orientation reversal. So I'm allowing things like Mobius bands, but instead I'm also putting in this extra framing relation that allows me to cancel a half twist and giving a factor of square root of the ordinary framing factor. But the most important ones are these two. So these two are the relations that did not exist in the ordinary Kauffman bracket skein module. So if this orange line is an edge of a boundary marking, if we have this just C-shaped tangle with states mu and nu, then it can be evaluated to a number which is 0 if mu and nu are the same, and it's some power of minus a squared if they are different. Also, we can pull a part of our stated tangle closer to a boundary marking, collide it, express it as a linear combination of the two stated tangles that we obtain in this way. So these two relations allows us to firstly just evaluate and get rid of all those just C-shaped tangles, state tangles, and also allows us to pull part of our stated tangle, collide it to the boundary marking, and basically express it in terms of like simpler pieces. Any questions so far? Okay. Yeah, so that was the definition of the stated skein module. Just like there's a skein algebra associated to surfaces, there is stated skein algebra associated to surfaces. So if we have an oriented surface, sigma, whose boundary consists of intervals, for instance, something like an n-gon, which is a disk with n punctures on the boundary, then we can firstly choose a set of marked points on the boundary consisting of 1 point from each interval on the boundary. And then we cross it with an interval I. So yeah, this is an example of a hexagon. So we choose a marked point just one mark point in each boundary interval. We cross it with I, then we get this boundary marking. And the stated skein algebra of this surface is just the stated skein module of this boundary marked three-manifold. And again, we can always stack along the interval direction, giving it an algebra structure. It's a unital associative algebra. So yeah, I mentioned earlier that we're using a definition that's slightly more general than the one that was previously considered by other people. And actually, that is the generalization I mentioned is that previously other people have considered the boundary markings, which are just disjoint unions of intervals, whereas here we are allowing this boundary markings to be a bipartite graph, just oriented bipartite graph. So we're allowing these vertices, and we actually gain quite a lot more information from that. And that can be summarized in this proposition. So the point is, if we have a boundary marking, let's say, look at this vertex of a boundary marking. It has degree 3. Then we can first delete a small neighborhood of this vertex. Then that's topologically equivalent to this picture where we have pulled out a small triangular prism. Then, because we can stack a triangular prism on top of this, this stated skein module is naturally a module over the stated skein algebra of a triangle. And this is true for each vertex of the boundary marking. So that makes the stated skein module of our boundary marks three-manifold a bimodule. It's a left module over the tensor products of all the stated skein algebras of polygons, one for each sink vertices. Right module over the same tensor products over polygons, one for each source vertices. Yeah, so we can think of the stated skein module as a bimodule over big tensor products of skein algebras. Is everything clear so far?
What's the difference between the stated skein algebra you've defined and stated SLN skein algebras?
Oh, this is SL2 skein, yeah, SL2. Everything I'm talking today is SL2.
Because you're using webs, I see, and those webs appear in the SL3 or SLN.
Oh, sorry, it's different things. So all these orange lines are boundary markings,
Okay.
meaning these are not skeins, where
Okay.
I think the webs you're talking about are elements of the skein.
Yeah.
These are always SL2. Any other questions? Okay. Yeah, and this is just one way of thinking about this bimodule structure. When I said isotopy of stated tangles, we don't allow the endpoints of a stated tangle to move across a vertex, but by using stated skein relations, so let's say in this example, we have a part of a stated tangle ending on this boundary marking with state mu. We can apply our one of the stated skein relations to collide this to this boundary marking and express it as a linear combination of it. And then we can look at this small stated tangle as an action of the corresponding element of a stated skein algebra to the stated skein module. So if we view these stated skein algebras for which this skein module is a bimodule of as coefficients, then we get some sort of skein relations where we can, as we slide the endpoint of a stated tangle across a vertex with coefficients in this stated skein algebra. So this is just one way to think about this bimodule structure. And yeah, this bimodule structure will play a very important role later. But for now, let me review the story in 2D. So probably the most important property of stated skein algebras is that they admit an algebra homomorphism called the splitting homomorphism. So let sigma be an oriented surface whose boundary consists of some unions of intervals. And let C be an ideal arc, meaning it's an arc whose endpoints are both punctures, something like this. And we can cut the surface sigma along this ideal arc, obtain a new surface, sigma prime. Then under this cutting, this theorem says that there's an algebra homomorphism from the stated skein algebra of the original surface to that of the new surface, sigma prime. And the way this homomorphism is constructed is in a very natural kind of state sum manner, meaning given any stated tangle in sigma times interval, we really cut that tangle along this ideal arc times interval, and we'll create a new tangle in sigma prime times interval. And then that's what I'm calling L prime. And then since in the newly cut endpoints of the tangle, we have to assign the states, we basically sum over all possible ways of assigning the states. We sum over all possible ways of assigning states to the newly cut end. Yeah, and the claim of this theorem is that this is a well-defined algebra homomorphism. Okay. From the existence of the splitting homomorphism alone, one can already get a lot of insights into the stated skein algebras. For instance, if we start from a bigon 2, then we can split a bigon along this ideal arc to create 2 copies of bigon. So the splitting homomorphism gives a homomorphism from the stated skein algebra of bigon to tensor products of 2 copies of it. And so it gives a stated skein algebra of bigon a co-algebra structure. And in fact, Constantine and Ley shows that these are in fact Hopf algebras, and as Hopf algebras, these are isomorphic to the quantized coordinate ring of SL2, which is Hopf dual of the UQSL2, the quantized universal enveloping algebra of SL2. Okay, that's nice. And we can also do similar splittings for any surface and for each choice of a boundary interval. So yeah, if this is an interval in the boundary of sigma, then likewise we can split along an ideal arc that's very close to that boundary interval, basically splitting off a bigon, and that gives this stated skein algebra of this surface sigma a co-module structure over this co-algebra, this SK algebra of the bigon. Yeah. And the last remark is that, so in this splitting homomorphism, okay, once we've split, then we're creating 2 new boundary intervals, like one on the left and the one on the right. And as I just mentioned, as I just remarked, for each boundary interval, we get a co-module structure on the stated skein algebra. So the stated skein algebra of sigma prime is going to be a bi-co-module over the stated skein algebra of a bigon, because we have a module structure, one on the left and one on the right. We have a co-module structure, one on the left and one on the right. And Constantino-Lay showed that the splitting map is actually an algebra isomorphism to the zeroth Hochschild cohomology, which is a submodule of the stated skein algebra of sigma prime. So really, but by using the stated skein algebras, one can really study skein algebras of surfaces by cutting it into simpler pieces and just understanding the constituent pieces. So this is the approach. Basically pioneered by Bonhoeffer Wang, Lay, and Constantino-Lay. Any questions so far? Okay. Even so, we can further simplify the skein algebras and modules by taking some nice quotients called reduced skein algebras and modules, which sometimes become almost commutative. So a stated tangle of the form, so it's an elementary tangle that looks like this or this when seen from outside of Y, we're going to call them bad arcs. So it must have this specific states. And these are the stated tangles that we want to take a quotient of. For instance, in case of stated skein algebras, the bad arcs in surface times interval are the ones of the form where, first of all, it's a elementary tangle just going around a puncture in the boundary, and the state must be in such a way that as we go counterclockwise, it goes from minus to plus. So these are the bad arcs. And the reduced skein algebra is, which I denote by this SK algebra, the overline. It's a quotient of the stated skein algebra of surface by the two-sided ideal generated by those bad arcs. And we can define the reduced skein modules in a similar way by killing those bad arcs. And the following proposition tells us that by taking this quotient, this reduced stated skein algebra often becomes almost commutative or sometimes even commutative. So for instance, in case of a bygone, I've remarked earlier that before taking this quotient, the stated skein algebra was isomorphic to the quantized coordinate ring of SL2. But by taking this quotient, it becomes really just a commutative ring, which is the Laurent polynomial ring in one variable. And this one variable can be represented by a tangle that's just a straight line connecting the two boundary intervals with signs plus plus. Its inverse is the one with signs minus minus. The ones with, say, plus minus or minus plus gets killed because those are bad arcs. The second proposition tells us what the reduced stated skein algebra of a triangle looks like. So the reduced stated skein algebra triangle turns out that it's a quantum torus, sometimes called the triangle algebra. So it has, it's an algebra generated by Q commuting or A commuting variables, alpha, beta, and gamma. So roughly alpha, beta, and gamma, these are variables associated to the three vertices of the triangle. So we can visualize this element alpha as a stated tangle around this vertex with signs plus plus, likewise beta this tangle, gamma this tangle. And they all commute up to this variable A. Meaning, yeah, as a vector space, or as a R module, it is spanned by monomials in alpha, beta, and gamma, and all these monomials basically commute up to some power of A. So it's something that's very easy to understand. Before telling you what the two-dimensional version of quantum trace map is, I also need this following lemma, which is an embedding of this quantum torus T. So I'm calling this reduced status skein algebra of a triangle math BBT, or triangle algebra. And this one with tilde is an extended triangle algebra, which, as you can see, in terms of generators and relations, it's given by exactly the same form. So it is actually isomorphic to the triangle algebra, the ordinary triangle algebra, but we are choosing a specific embedding that's not an isomorphism. So, point is, these variables A, B, and C can be thought of as associated to the edges instead of vertices, and this embedding is given by maps, where, so for each generator, say alpha is associated to this vertex. It's adjacent to these two edges, B and C, so it's mapped to the file-ordered product of B and A, and likewise for the other ones. And it turns out that this is an algebra embedding. And now I can tell you what the two-dimensional quantum trace map is, which was originally constructed by Banohan and Wang, and kind of reinterpreted in terms of the status skein algebras by Constantin and Ley. So let sigma be an ideally triangulated surface. Then we can first apply the splitting map to get a homomorphism from the status skein algebra, or the reduced status skein algebra, to the tensor products of the triangle algebras. So remember that the triangle algebras are the reduced status skein algebras associated to triangles. And since we're splitting into triangles, this is what we get. And then we compose it with the embedding that we constructed just now. We embed it into the tensor products of extended triangle algebras. And it turns out that this composition, which is an algebra homomorphism from the skein algebra, and it turns out that the image lies in what's sometimes called the quantum Teichmüller space, or more precisely, it's something that's known as the square root Chekhov-Fock algebra. I don't think I'll have time to tell you in detail what the quantum Teichmüller space is, but just very roughly, in Teichmüller space, there are coordinates called shear coordinates associated to each edge of ideal triangulation of the surface. And a quantum Teichmüller space is basically a quantum torus, basically quantizing those coordinates to Q commuting variables. And yeah, the image of this map is that. And so, this 2D quantum trace map, originally constructed by Banohan and Wang, tells us how the two quantizations of the character varieties of surfaces are related to each other. That was a review of the 2D quantum trace map. Are there any questions? Okay. Then let me tell you how we can generalize this construction to 3D. A three-dimensional analog of quantum Teichmüller space is what's sometimes known as the quantum gluing module. which is a two-sided quotient of a quantum torus. And this quantum torus consists of Laurent polynomials in quantized shape parameters. Just like in case of Teichmüller space, there are these coordinates called shear coordinates associated to each edge. In case of three-dimensional hyperbolic geometry, there are these coordinates, or called shape parameters, associated to each dihedral angle of the ideal tetrahedron. So roughly, so we start from an ideally triangulated three-manifold. So we've cut our three-manifold into ideal tetrahedra. Then for each ideal tetrahedron, there are 3 pairs of opposite edges, right? So there are 6 edges in total, so there are 3 pairs of opposite edges. This is just for convenience of notation, I'm gonna call one of the pairs Z, and in clockwise we label them by Z prime and Z double prime. So these are, classically, these are some complex parameters that determines the shape of this hyperbolic ideal tetrahedron. And as we quantize, these shape parameters become Q-commuting variables. These are variables now commuting up to some factor. In other words, these Z hat, Z prime hat, and Z double prime hat, they generate a quantum torus. But these are not all independent variables because, first of all, even classically, these parameters must satisfy certain relations, namely that the product of these 3 complex numbers must be -1, and also that Z prime is 1 minus Z inverse, etc. And also, as we glue these hyperbolic ideal tetrahedra together, on each edge, the dihedral angles must add up to 2 pi to give a complete hyperbolic structure. It shouldn't have any cone angle, meaning it must satisfy some gluing equations. At the level of quantization, these are given by these relations that must be satisfied by these variables. Yeah, so these are certain relations that we need to take quotient by, and the quantum gluing module is basically the quantum torus generated by all these variables, and we're taking a 2-sided quotient. On the left side, we take quotients by these relations. On the right side, we take quotients by these relations. That's what's known as the quantum gluing module. Okay, so the problem we wanted to solve is to construct some homomorphism from the skein module to the quantum gluing module. And here, just like how in 2-dimensional quantum trace map, actually the map we get is not exactly to the ordinary quantum Teichmüller space, but rather quantum torus and consisting of Laurent polynomials and square roots of the quantized shear parameters. We might need some square root variables, so that's the problem we wanted to solve. So the first step would be to come up with an analog of the splitting map in the 3-dimensional setting, because that was the first key ingredient in the construction of this 2D quantum trace map, right? The first key ingredient was the splitting map, and the second key ingredient was, after passing through the reduced skein module, and the second key ingredient was this construction of this embedding. So for the first part, to state the splitting map, splitting homomorphism, we've introduced this notion of combinatorial foliation, motivated by some constructions in mathematical physics, namely the 2D and 3D, three-dimensional spectral networks. Okay, so what's a combinatorial foliation of a surface? It's a decomposition of a surface into pieces, each of which look like this. So it's a quadrilateral with two punctures. Two of the vertices are punctures. And we're also putting marking. We're putting a orange marking going from one vertex to another. And as we glue these elementary quadrilaterals, that's what I call it, as we glue these quadrilaterals, we require that when two edges are glued together, the orange vertex, if it was a sink in one quadrilateral, it must remain sink. And if it's a source in one quadrilateral, it must be a source in others as well. So here are some examples of combinatorially foliated surfaces. This is just the elementary quadrilateral itself. This is just one where we have glued two of them, and note that this vertex is a sink in both quadrilaterals. And this is just another way of gluing these two, and we can glue three of them to make a triangle with this particular marking. And we call this a combinatorial foliation because we can associate a topological one-dimensional foliation, an actual foliation of this quadrilateral, for which the generic leaves are in one-to-one correspondence to the interior points of this marking. Okay. Now, we've shown the theorem. It's a version of a splitting map for 3D, and so it works in the following setting. So starting from a boundary marked 3 manifold, we split it along a combinatorially foliated surface. So just to give you a sense of what it's like, let's say we have our 3 manifold Y. It might have some boundary markings. Something like this, whatever. And let's say we're cutting this 3 manifold along a combinatorially foliated surface. Meaning, as I've shown you, the definition of combinatorially foliation comes with a boundary marking. So it's going to have some marking inside. Something like this. And once we've split it, we're going to get, let's say we get two disconnected pieces, Y1 and Y2. Individually, they're going to have this new boundary marking, which I call gamma 1 and gamma 2. And the theorem is that there is a bimodule homomorphism from the stated skein module of this boundary marked 3 manifold to the relative tensor products of these two skein modules. And what I mean by relative tensor product is, so this is not an ordinary tensor product as R modules, but rather it's more like taking tensor products of two modules over the same algebra. So remember that the skein module, I told you that it has a module structure for each vertex of the boundary marking. And once we've split it like this, then for each vertex of the marking on the combinatorially foliated surface, we get a module structure, both on this skein module of y1 and also for y2. And somehow the action must be compatible. And that's basically what this quotient we're taking is. Yeah, again, morally, this relative tensor product is really just the tensor product of two modules over the same algebra. We want the algebra action on the left to be the same as the algebra action on the right. So we have the splitting map. And now we want to use this splitting map to actually construct a homomorphism from the skein module to the quantum gluing module. For that, we need to start from an ideal triangulation of Y. And it turns out that a more natural way of splitting Y is not into ideal tetrahedra, but actually into what we call phase suspensions. So what's a phase suspension? So let's say this left picture is part of an ideal triangulation. So we have two ideal tetrahedra glued along a face, a triangle. Then we can take a suspension of this face, basically taking the join of this triangle with the two barycenters of the top and the bottom tetrahedra. This is what we call the phase suspension, and we're going to put this specific boundary marking to each phase suspension. Note that this boundary marking has two sink vertices of degree 3 and 3 source vertices of degree 2. Okay, so this is a corollary of this existence of splitting map. So if we apply that splitting theorem to this particular splitting into phase suspensions, then we get a map from, okay, and again, we can work with the reduced skein modules by passing to the quotient. We get a splitting map from the reduced skein module Y to the relative tensor product of reduced skein modules of the phase suspensions. And by this relative tensor product, we mean we're taking a quotient of the ordinary tensor product as R modules by the following relations. The first relation tells us that around each edge of a triangulation, there's going to be some number of phase suspensions glued around that edge, and there's going to be corresponding action of the skein algebra of a bygone, because so remember that the skein module of a boundary marked three manifold has naturally a bimodal structure. And in this case in particular, it has a right module structure, so it has a right action by the skein algebra of a bygone, because it has degree 2, at each edge. And there are 3 of them. So we have this relation between these actions for each internal edge. And likewise, around the barycenter, or more precisely, around each line connecting a vertex and a barycenter, what we call a vertex cone. Around each vertex cone, we have 3 phase suspensions glued around the vertex cone. And there we have some extra relations. And the point is, these relations look exactly like the relations that we have among the quantized shape parameters. So first of all, we have the gluing relations that the product of the quantized shape parameters, the Weyl ordered product, evaluates to some number that basically corresponds to this first relation. We also have the relation saying that the Weyl ordered product of three quantized shape parameters of the same tetrahedron evaluates to some number. That's basically this relation. And lastly, we have this relation, sometimes called the Lagrangian relations. So we have this three-term relation, z hat prime equals 1 minus z hat inverse. And that three-term relation basically corresponds to this three-term relation. So that will be an important ingredient. We just need one more thing before finishing our construction, which is, okay, so we have split it, we have split our three-manifold into phase suspensions. Now we have to analyze what the stated skein module of each phase suspension looked like. And we have determined what it is. So actually we have determined it for any three ball with whose boundary is combinatorially foliated. And a phase suspension is an example of it. So for any three ball with boundary marking, we've shown that it's actually, as a body module, it's a cyclic module, so it's generated by the empty skein. And the relations is exactly the ideal generated by the relations given by these forms. So we have a structure theorem, and in particular, if we apply that to the reduced skein module of a phase suspension, we have this nice presentation of the reduced stated skein module of a phase suspension. It's a tensor product of two triangle algebras and tensor product of three biangle algebras modulo these relations. And just like there was this embedding of a triangle algebra to an extended triangle algebra, we have an embedding of the reduced skein module of phase suspension to the tensor product of two extended triangle algebras. So there's a bi-module embedding, basically sending the empty skein to 1. And okay, we can put now everything together. So we starting from a skein module of y, which if it doesn't have a boundary, it's the same thing as a reduced skein module of y. We apply the splitting map, expressing it as a relative tensor product of reduced skein modules of phase suspensions, which is a quotient of the ordinary tensor product as R modules of skein modules, reduced skein modules of phase suspensions. And we had this embedding, bi-module embedding, which we denoted by TR trace of SF so we're thinking of it as a quantum trace map for a single phase suspension. So that gives an bi-module embedding on this top row. And then we want to take some quotient going down to this part that allows us to make this homomorphism work. So yeah, basically this quotient is determined to be just a quotient by the images of the relations that we have to take into this vertical arrow. And yeah, and this composition is the 3D quantum trace map. And yeah, and the image of this 3D quantum trace map, it turns out to lie in the square root quantum gluing module for the reason that I told you earlier, that the gluing relations that we see, these relations that we have under splitting, they look exactly like the relations among the quantized shape parameters, and that's exactly why this construction works. Yeah. So the image So we have constructed a map from the Kauffman bracket skein module Y to the square root quantum gluing module Y, which consists of Laurent polynomials and square roots of the quantized shape parameters. Yeah, that's basically all I wanted to say. Okay, let me stop here. I'm happy to answer any questions.
What are the questions? So can you turn it to some more basic invariants? In the sense of some two numerical ones.
Yeah, so I think one application of this would be that, so there are these state integral models giving some version of complex Chern-Simons theory. One can use this quantum trace map to insert line operators in the state integral model. So if we want to insert a Wilson line, say associated to some skein, then we can just compute the image under this 3D quantum trace map. That's already expressed in terms of these quantized shape parameters. So we can just put it in the state integral model. Yeah, so it basically tells us like what's exactly the homomorphism. It basically tells us how to insert Wilson lines in state integral models or DGG theories.
What kind, can you engineer any kind of Wilson line?
Sorry?
Can you engineer any Wilson line?
Any Wilson lines in SL2.
I don't see any urgent questions. Maybe there are more during the coffee break, which we hopefully follow. So let's thank Sam again.